Dr. R. Hemavati is an assistant professor in mathematics in Queen Mary's, Chennai. She has specialized on functional analysis. Having 12 years of experience in teaching, she has won various awards for her performance. She has published papers in 14 international journals, 3 national journals, and has presented papers in 10 international and in 5 national conferences. She is also one of the editors for an international journal.
Welcome to UGC lecture series. In this subject statistical methods 2, and in this session we are going to study about a large sample test of significance for difference of standard deviations and single proportion. In the earlier sessions we studied about the attributes and a test of significance sampling distribution. We have in continuance with the topic of large sample, we have already dealt with test of significance for single mean and difference of means, and test of significance for a specified standard deviation. So, in continuance with that, in this session we will study about large sample test of difference of standard deviation and test of significance for single proportion and test of significance for difference of proportion. So, interval estimation in this regard is also done. First of all, large sample test for equality of 2 standard deviations. The test also may be termed as test of difference of 2 standard deviations. So, to start with, let S1 and S2 be the standard deviations of 2 samples of size N1 and N2 respectively from 2 populations with standard deviation sigma 1 and sigma 2 respectively. Then the formula for test for equality of 2 standard deviations, which is a normalized form, is given in the format as Z is equal to S1 minus S2 divided by root of S1 square by 2 N1 plus S2 square by 2 N2, where this S1 S2 stands for sample standard deviations. Already 7 examples have been worked out in a large sample test of significance in the earlier sessions. So, in continuance with the 7 sample, the next example is example 8. 2 random samples of sizes 50 each were drawn from 2 populations and the standard deviations were formed to be 4.5 and 3.5. Is it reasonable to suppose that the samples belong to the population with the same standard deviations? So, first of all, we will write down information given in the question. There are 2 samples given, therefore, we will call it as sample 1 and sample 2. Both the samples are of sizes 50, therefore, N1 is 50 and N2 is also equal to 50. Both the samples were drawn from the 2 population and the STs of the samples have been given as S1 is equal to 4.5 and S2 is equal to 3.5 respectively. Is it reasonable to suppose that the samples belong to the population with same SD? You are asked to test the equality of 2 standard deviations of the populations. So, let us start with the procedure for testing of significance. First step is setting up null hypothesis, second step setting up alternative hypothesis, third step is level of significance, fourth step is computing the statistic, and fifth step is conclusion. So, first we start with H naught, which is null hypothesis, which says sigma 1 is equal to sigma 2. That is the 2 population standard deviations are equal, or according to the question we may say that the samples have been taken from population with same SD. Same SDs. This is what you have been asked to verify, and then H1, nothing is specified in the question about whether first population SD is greater than second population SD, or second population SD is greater than first population SD. Since nothing has been specified, I will just take sigma 1 is not equal to sigma 2, and this happens to be a two-tailed test. Okay. So, the complementary statement for H naught here, the samples are not taken from the population with the same SD, same standard deviations. Next, level of significance fixed is 5%. Then step 4 is the calculation part, where we have to calculate the Z value using the formula for test of equality of standard deviations. So, S1 minus S2 divided by root of S1 square by 2n1 plus S2 square by 2n2, where S1 is given to be 4.5 and S2 is given to be 3.5. So, 4.5 minus 3.5 divided by 4.5 whole square by 2 into n1 is 50 plus 3.5 whole square by 2 into n2 is also 50, and this value comes to be equal to 1.75413. Okay, and this is the calculated value, which calculated Z at 5% is 1.75413 within modulus, so 1.754. Next, step 5 is conclusion, where we have to compare the calculated value and the tabulated value. Calculated Z is 5% is 1.754, which just now calculated, and then tabulated Z is taken from the tables which I have shown in one of the previous sessions, that is tabulated Z at 5% is 1.96. Here, when you compare the two values, the calculated value is lesser than tabulated value. Therefore, 1.754 is lesser than 1.96. So, calculated Z is less than tabulated Z. Therefore, H naught is accepted. H naught is accepted, which means the samples have been taken from, what is the statement of H naught? That should be written as conclusion here. The samples have been taken from the population with same STs, with the same STs. Okay. Now we have answered to the question given. Therefore, the conclusion is the samples are taken from the population with same STs. Next, sampling of attributes. Actually, we are in large sample test, and the whole statistical methods too refers to testing of significance with respect to large sample and with respect to small sample. In large sample, we are dealing with Z test, and in small sample you are going to deal with T, F and chi-square. So, when the whole topic is about testing of significance, why did we study the attributes, which we have already done in the previous sessions? This is how attributes is used for a sampling, that is a sampling of attributes. Now, consider the sampling from a population which is divided into two mutually exclusive and collectively exhaustive classes. And this kind of division we have already seen in the attributes session as dichotomous classification. The whole population is divided into two categories, one possessing the attribute A and other class not possessing the attribute A. Okay, this kind of classification is called dichotomous classification. This we have already seen in the previous sessions. So, with respect to the sampling, the whole class is divided into two parts, one possessing and another not possessing. Then note down the number of persons possessing the attribute in the sample of size n. You have taken a sample of size n and the whole sample is divided into two parts, one possessing and another not possessing, and then note down the number of persons possessing the attribute in the sample of size n. So, the presence of an attribute in sampled unit may be termed as success and its absence as failure. In this case, a sample of n observations is identified with that of a series of n by independent Bernoulli trials with constant probability p of success for each trial. Then the probability will be given by the binomial distribution using the various combination of the cases where the probability distribution will be given as p of x is equal to x is ncx p power x q power n minus x, because the sample of n observation is compared with n independent trials. N independent Bernoulli trials becomes a binomial distribution, okay, where x represent the number of successes. This number of successes is what is the number of persons possessing the attribute in the sample of size n, and this is actually x, because success is termed as possessing the attribute. Then what is x by n will represent? X by n will represent the proportion of a success. That is what is represented as a small p. Small p represent proportion of success and it is taken from a sample of n items. X represent the number of successes. So, p stands for proportion of success with respect to sample, therefore, it will be called as a sample proportion of success. When small p is called a sample proportion of success, then capital P will be called as a population proportion of success. And then Q will have the usual meanings. Q is equal to 1 minus P. This we have already seen in binomial distribution. Q stands for proportion of failure. Proportion of failure in the sense proportion of the number of persons not possessing the attribute A. Okay. Similarly, Q will have the same meaning as in the binomial distribution. Q is equal to 1 minus P. Q stands for the proportion of failure. Proportion of failure in the sense number of persons in the sample of size n not possessing the attribute. Number of persons not possessing the attribute will be called as when you take the proportion, it becomes a Q. Q is equal to 1 minus P. Then capital Q will be population proportion of failure, right? Population proportion of failure. That is the proportion of the persons, whole persons not possessing the attribute A. Now comes the test for single proportion. So, now P is taken as a sample proportion, capital P is taken as population proportion, Q is equal to 1 minus P and capital Q is equal to 1 minus capital P. Then where does the normalization of the variable concerned occurs and how we convert the whole sampling of attributes to test of single proportion is now done through Z formula. Z is equal to T minus E of T by standard error of T. The variable is x. X is the number of successes out of n sampling distribution, n samples. Therefore, x minus np. Np is the mean of binomial distribution and standard error of T is the standard deviation of binomial distribution, which is root of npq. Then when you take the n outside, it becomes n into x by n minus capital P divided by n into root of npq. Okay. So, this is equal to n into small p minus capital P divided by root of npq. Taking that n to the denominator, p minus capital P divided by root of npq by n. This becomes p minus capital P divided by root of pq by n. So, now the normalization of this variable with respect to the attribute, possessing the attribute and not possessing the attribute, is converted to test for single proportion, and the formula has now become Z is equal to small p minus capital P divided by root of PQ by N, where capital Q is equal to 1 minus capital P and N stands for sample size. Okay. Probable limits for proportion, which is a population proportion, it becomes like expectation of x plus or minus 3 into root of variance of x. Just simplifying this, it becomes capital P plus or minus 3 into root of PQ by N. Okay, these are the probable limits for capital P. Okay, and the usual interval estimation for the population proportion, that is 95% confidence limits, 99% confidence limits, will be derived using the formula Z is equal to small p minus capital P divided by root of PQ by N. Continuance with the examples, 8 examples have been already worked out in large sample test, where we have done problems in test for a single mean, test for difference of means, test for specified standard deviation and test for difference of standard deviation. Now, this problem is with respect to test of significance for single proportion. What does the example says? In a sample of 1000 people in Tamil Nadu, 540 are rice eaters and the rest are wheat eaters. Can we assume that both rice and wheat are equally popular in this state at 1% level of significance? Okay. So, the whole population is divided into two classes. One class are rice eaters and another class are not rice eaters, but they are wheat eaters. So, the rice eaters are taken as the persons possessing the attribute A. A is taken as rice eaters. Okay. And then we are asked to check whether they are equally popular in the whole state. First of all, take the sample. The sample is size is 1000 and 540 are rice eaters. So, sample proportion of rice eaters are 540 divided by 1000. They are represented as P. We will stick on to one attribute, that is rice eaters, and another class of people are not rice eaters. Okay. So, small p is equal to 540 divided by 1000, which is equal to 0.54. Therefore, small q will be equal to 1 minus p 1 minus 0.54, which is equal to 0.46. Then you are asked to verify whether they are both equally popular in the state. So, the whole population is divided into two parts, right? One are rice eaters, they are attributes A, and not rice eaters, but wheat eaters. Okay. So, since the population is divided into two parts, the population proportion of rice eaters will be 1 by 2, and this is represented as capital P. So, capital Q is equal to 1 minus P is equal to 1 by 2. So, now we will start the exact procedure for testing of significance. Step 1 is setting up of H naught. You are asked to verify whether they are equally popular. Therefore, we will set up H naught as capital P is equal to 1 by 2, that is rice eaters, and you are fixing up the value as 1 by 2. It means whole population is divided into two classes, one processing rice eaters and another one wheat eaters. Therefore, you should take the H naught also as rice eaters and wheat eaters are equally popular. popular in the state. Therefore, step 1 will be H1 P not equal to 1 by 2. So, in words rice and wheat eaters are not equally popular. Step 3, the level of significance fixed in the question is 1%. You are asked to verify at 1%. And then step 4. Step 4 is a calculation part. Z is equal to small p minus capital P divided by root of PQ by N. Small p is 0.54 we have got, and capital P is 1 by 2 which is 0.5 divided by root of 0.5 into 0.5. N value is 1000. And this answer comes to be equal to 0.04 divided by 0.25 by 1000 is equal to, the value is 2.532. 2.532. Therefore, calculated Z at 1% is equal to 2.532. Therefore, now we have come to the conclusion part where the calculated Z and tabulated Z are compared. So, calculated Z is 2.532 and tabulated Z at 1% is referred from the tables which I have shown in one of the previous sessions, which is equal to 2.58. Now, therefore, the calculated value happens to be lesser than 2.532 is lesser than 2.52. Tabulated is at 1%. Therefore, H naught is accepted in the sense both rice eaters and wheat eaters are equally popular. Popular in the state. You have to always mention the level of significance also, the state at 1% level of significance. Okay. Next, a random sample of 500 pineapples was taken from a large consignment and 65 were found to be bad. Show that the standard error of the proportion of bad ones in a sample of this size is 0.015 and deduce that the percentage of bad pineapples in the consignment is almost certainly lies between 8.5 and 17.5. This is also a problem of single proportion, wherein you are not asked to test the significance, but you are asked to find out a standard error and the probable limits for that. Okay. So, first of all, we will write down the informations from the question. Okay. Sample of 500 pineapples. Therefore, N is equal to 500, and out of 500, 65 are found to be bad. Therefore, P is equal to sample proportion of bad pineapples. How many are there? 65. Therefore, proportion means 65 by 500, which is equal to 0.13. Therefore, Q is equal to 1 minus P is equal to 1 minus 0.13 is equal to 0.87. Then, capital P is equal to a population proportion of bad pineapples. Okay. And since it is not given, we will take the estimate of the population proportion as a small p. Small p is equal to 0.13. Because population proportion is not given, we have to take its estimate only. So, similarly, capital Q cap is equal to small q is equal to 0.87. Now, you are asked to find out the standard error. A standard error formula is standard error of proportion is equal to root of PQ by n. Since capital P and capital Q value is not given, we will take its cap values. Cap values means capital P cap and capital Q cap, they are called estimates of the population proportions. Okay. So, this is equal to root of 0.13 into 0.87 divided by 500, and this value comes to be equal to 0.015. Now, we have got the answer for standard error of a proportion of bad pineapples. Then you are also asked to find out the limits for probable limits for the consignment of bad pineapples. So, probable limits formula we have seen, probable limits formula is P plus or minus 3 into root of PQ by n. Since P is not directly available, you have to take its cap values P cap Q cap by n, and this value is 0.13 plus or minus 3 into root of 0.13 into 0.87 divided by 500, and the values are 0.13 plus or minus 0.045. So, the plus value, one plus value will be 0.175 and minus value will be, minus means 0.13 minus 0.045 will be 0.085 comma 0.175. Okay. These are the probable limits of the consignment of bad pineapples. In this session, we have dealt with problems where test for problems in large sample test for equality of standard deviations, and then after discussing the sampling of attributes, we have derived the formula for test for single proportion, and also some problems have been worked out in large sample test for single proportion, and the probable limits for proportion is also discussed. So, based on the discussion in this session, the following questions may be posed. Derive the formula for test of significance for single proportion using sampling of attributes, that is the derivation Z is equal to P minus capital P divided by root of PQ by n. That derivation using attributes you have to derive it. A brief large sample test for equality of standard deviations, it means you have to brief how H naught, H1 and were set up for the test for equality of standard deviations, and what is meant by probable limits. Thank you.